Welcome back everyone. In this lecture I am going to prove the Frobenius theorem on this group determinants. So, let us first recall what is the group determinant. So, we start with a finite group G and then we just take these indeterminants x g, g in G. So, for each element of G we take this commuting variable x g. So, then look at this matrix capital X G given by x g h inverse where G and H runs over G cross G. So, it is G cross G indexed matrix whose G H entry is, so G H entry is given by x G H inverse. So, now what is the group determinant? The group determinant is nothing but the determinant of this matrix. The determinant of x g is either called group determinant or Frobenius determinant. So, this is what the group determinant. So, now what is Frobenius theorem actually guarantees you that. So, it generalizes the Dedekind's theorem. So, which we stated for abelian groups. So, if we take G finite abelian group, then this group determinant actually factorize into these linear factors. But when we are dealing with non-abelian group, we will get slightly different factors and of course, they are related to irreducible representations. So, let me just state the result. The group determinant x g, so we can write it as product of r number of these factors where the powers of these factors also will appear. So, it is product of p j x bar power the degree of this p j. So, where j runs for from 1 to 1. So, this is the factorization that we will be getting. So, here what are this p j x bar? They are some pairwise non-proportional irreducible polynomials and this R is indeed the number of conjugacy classes of G. So, where this p j x bar, they are pairwise non-proportional irreducible polynomials. Of course, irreducible in these variables x g, g in G and this R is the number of conjugacy classes of G. So, it gives very explicit factorization of this determinant of x g in terms of some irreducible polynomials. So, we can actually make some of the things very explicit. We will see in a minute that the degree of this p j. So, this is going to be related to the dimension of the irreducible representation. So, if we take this V 1 etcetera V r to be the set of inequivalent irreducible representations. So, let us say this is exactly the G hat. So, this is the set of inequivalent irreducible, of course, 5 dimensional irreducible representations of G. So, then this P j is indeed related to V j and the degree of P j is exactly given by the dimension of V j, which is the degree of that irreducible representation. Okay, this will be made very explicit while proving the theorem. But to prove this theorem, we need many preparatory results. So, maybe like let me do one by one and then finally, I will actually give the proof of this Frobenius theorem. So, the very first result that we needed is the density theorem. So, let me first state the density theorem and then I will actually prove that theorem. So, the statement of the density theorem is indeed actually very simple because we are working over complex numbers. So, I am going to only state the density theorem for this particular version that works for complex numbers. So, in very simple terms, what is the density theorem? So, the density theorem that tells us about surjectivity of some maps. So, here is the density theorem. So, let us start with V being finite dimensional irreducible representations of this CG over C. So, let us fix this capital A by CG. We have already seen that the representations of G and representations of CG, they are equivalent. So, now what we are going to do? We are going to take this V, this is a finite dimensional irreducible representation of A over C. So, let us say the representation map is given by rho, which is a map from CG to, now we can think as map from CG to the endomorphism of V. Okay. So, if I am thinking it as a representation of CG, it is a group algebra homomorphism from CG to endomorphism of V. Basically, the density theorem asserts that this map must be surjective. So, then this map is indeed a surjective map. So, that is what density theorem actually asserts. So, let us actually write down somewhat other version of this density theorem. So, that is what most of the time stated in the books, but an important corollary is this theorem. So, this is why this is called density theorem, because the image of CG exhausts the entire endomorphism of V. So, let us write down another version that actually kind of gives immediately the version that I wrote. So, as before, take V to be finite dimensional irreducible representation of A, where A is CG. So, now let us fix some n number of linearly independent vectors in capital V. So, you take V1 etc. Vn. So, this is subset of V, this is linearly independent. So, we are not assuming anything about n being the dimension of V or anything. So, all we know that n is less than or equal to the dimension of V. So, now this is given. So, then what density theorem guarantees us that for any choice of vectors W1 etc. Wn in V. So, for any choice of vectors W1 etc. Wn V. So, we can always find some A in capital A such that when you act A on Vi, you get exactly Wi, and this is true for all I. So, this is what the version of density theorem actually tells. Okay. So, this you can call it as density theorem. So, equivalently, if you think about it in terms of the representations, so we can actually look at this direct sum of n copies of V. So, we can look at this n copies. Then it is clear that this vector V1 etc. Vn, this is indeed lying here. So, this is indeed the set of vectors V1 etc. Vn, that is the given set of linearly independent vectors. So, then we can view this tuple as an element of this direct sum of V n copies. So, then we can rewrite this statement as follows. So, this statement. So, then basically what we are saying, there exists A in capital A such that when you take A and then apply it on this n vector V1 etc. Vn, then you get this W1 etc. Wn. So, that is what it guarantees. So, on other words, if I take this capital A and then generate this sub representation of this v direct sum n with this cyclic vector v1 etc. vn. So, then this sub representation is going to be that entire representation v direct sum n. So, this is equivalent way of stating it. So, basically this one single vector v1 etc. vn generates cyclically the entire v direct sum n. So, that is what density theorem guarantees us. Okay, so, let us prove this equivalent version. So, as before, like we take this v to be v1 etc. vn, this n tuple of vectors which is given to us. So, which is lying inside v direct sum n. Since v is CG representation, v direct sum n is also CG representation. So, now what we can do, we can look at this AV, so which is sub representation generated by v inside this v direct sum n. So, this is a sub representation. Indeed, our claim is this AV is exactly v direct sum n. So, now note that AV by definition you take all possible action of A on this cyclic vector v1 etc. vn, but since we are working in the direct sum, it will act on the individual coordinates. So, this is going to give us AV1 etc. AVn where A varies over capital V. Okay. So, this is our sub representation AV. So, now our claim is AV is exactly v direct sum. Suppose not, what will happen? Suppose we assume that AV is properly contained in v direct sum n. So, then we can actually look at this sub representation, since CG is semi simple, because we already proved that any finite dimensional representation must be completely reducible. So, now given this sub representation of this v direct sum n, we will have CG complement of that. So, we can write this v direct sum n as AV direct sum w for some A representation, A sub representation w of this v direct sum n. So, this is possible because we are working with finite group G. So, now let us look at that equation. So, we have AV direct sum w which is given by this v direct sum n. So, now this actually allows us to define this projection on w. So, if we consider this projection on w, then this is a map from v direct sum n to w. So, basically any element here, it is going to be written as some x plus y with x is coming from AV and y is coming from w, and this is actually unique choice for us. So, then you take this x plus y and then map it to y. So, this is the projection that we are talking about. So, now it is clear that pi w of this AV is going to be 0. So, this projection satisfies this important property. So, now since AV is proper, so since AV is proper inside v direct sum n, that would imply that w is indeed non-zero sub representation. Since w is non-zero representation, so we can be able to pick a coordinate projection that is actually non-zero on this w. So, what we do, we pick this k such that you look at this pk, which is the kth coordinate projection, and that actually maps this v direct sum n to this kth coordinate v. So, you take for example, W1 etc. Wn, and then this is mapped to Wk under this kth coordinate projection. And note that all these maps pi w and this Pk, all of them are indeed G maps or Cg maps. So, they are all homomorphism of representations. So, now if we use that, then what happens? So, you have this map from V direct sum n to W, and then you have this projection restricted to W. So, you take Pk restricted to W and then look at this pi W. Now, look at the composition, call it pi. Okay. What is pi? Pi is the composition. You first take this Pkw composition with pi W. So, then what are the properties of this pi? Pi is indeed a CG map, that means it is a map between the representations, and the important thing about pi is that because it is a composition of projection on W and Pk. So, clearly that pi of AV is going to be 0 for all A in A. So, that is if you take pi, apply it on capital AV, so that is going to be 0, because that is the property of this pi W. So, now if you are taking some W in W, then what will happen? So, if you take pi W, so this is going to be exactly given by Pkw, because pi W restricted to W is indeed identity on W. So, using this you can conclude this. So, in particularly pi is actually non-zero map. So, that is the important thing. So, pi is indeed non-zero map, because Pk is non-zero map. So, now we got this very interesting CG map, that is actually from V direct sum n to V, that satisfies this property. But what do we know about this endomorphism that commutes with the action of CG? Since V is irreducible, so we can actually tell something more about this endomorphism. So, note that pi is inside endomorphism of A V direct sum n V. Now, this direct sum and endomorphism commutes. So, this you can write it as direct sum of I range from 1 to n endomorphism of A V comma V. So, now what Schur's lemma says us? So, Schur's lemma guarantees that this is indeed one dimensional. Okay. This is from Schur's lemma. So, that means what can I say about this endomorphism of V comma V? So, this is exactly given by this one dimensional space spanned by the identity of V. Okay. So, that means if we rewrite this direct sum, this is going to be direct sum of this C identity V, where I range from 1 to n. So, that means this pi must be given by this direct sum of this scalar maps. So, pi is given by lambda 1 times identity on the first coordinate, direct sum etc., direct sum lambda n identity on the nth coordinate. So, this is how the pi looks like. So, there exist lambda 1 etc., lambda n coming from C such that this holds. Okay. So, this is kind of very strong restriction. So, now if we actually use this restriction and then rewrite what value pi can take, you can see that pi of u1 etc. un is going to be exactly equal to lambda 1 u1 plus etc. plus lambda n un for u1 etc. un coming from capital V. So, this is the property that we have, but note that pi restricted on AV is 0. So, if I take some A in capital A, So, then if I evaluate pi of a v, so which is going to be pi of a v 1 comma etcetera a v n. So, that is going to be on one side lambda 1 a v 1 plus etcetera plus lambda n a v n. On the other hand side, this is 0 by definition of pi. So, that tells you that you have this lambda 1 a v 1 plus etcetera plus lambda n a v n is indeed 0, and this is 0 for all a in capital A, but since a is unital, I can take a to be small a to be this unit element in C G. So, that would imply that we have this linear relations among this V 1 etcetera V n. But since pi is non-zero, then it is clear that this lambda i's they cannot be actually, not all of them are 0. So, these are not all of them are 0. So, that kind of gives kind of contradiction here, because we arrived some linear relation among V 1 etcetera V n. So, this is contradiction to the fact that V A is given to be linearly independent. So, this actually kind of completes the proof of density theorem. So, now if you go back to the original statement, so this can be proved just by taking n to be the dimension of V. So, now once you take n to be dimension of V, then V 1 etcetera V n becomes basis. So, V 1 etcetera V n. So, this becomes basis of capital V. So, now the density theorem, the second version, tells you that given any W n etcetera W n, we have A in A such that A V I is given to be W I. So, that tells you that this map that we have is indeed surjective map. So, this proves the density theorem. So, I will tell you later like where the density theorem will be playing a crucial role in proving Frobenius theorem. So, we need it to talk about the irreducibility of the polynomials that are appearing in the factorization. Okay. So, since we are actually talking about irreducibility, so let us actually get a criterion for irreducibility. So, since we are talking about the determinants, it is natural to consider the determinant of some y I j, where y I j's are variables, and then see that determinant of that y I j, that is indeed an irreducible polynomial in y I j. It is a very simple lemma, but anyway let me state and prove. So, what we are considering, so you take capital Y, this is the matrix given by this y I j, where these y I j's are like n square number of variables. So, this y I j are variables, of course commuting variables. So, now what we can do, given this data, we can actually construct this determinant of y. So, this is indeed an irreducible homogeneous polynomial in this y I j, irreducible homogeneous polynomial in y I j. So, I will leave it to you to think about why it is homogeneous. So, it is actually immediate from the definition. So, check that determinant y is indeed homogeneous in y I j. Okay. So, this is something like you can check directly. And another important thing about this homogeneous polynomials, so if you take any factor of homogeneous polynomial, that is also supposed to be homogeneous. So, any factor of an homogeneous polynomial must be homogeneous. So, that is again easy thing to check. Okay, I will leave it to you to check these two facts. So, now let us see like why the determinant of y is indeed irreducible polynomial in yij. So, there are many different proofs that one can give, but let me actually use this proof that is given in Ettinghoff. So, by specializing these variables yij to some particular other variables, then we will be able to conclude that the resulted polynomial will be irreducible, and that would actually tell you that the original polynomial must be irreducible. So, what is the specialization that we are actually talking about? So, let us take these variables, let us call it x. So, this is the new set of variables. So, they are obtained by substituting on the diagonal you put t for all I in n, and then when you look at this I plus 1. So, this is that off diagonal above the diagonal. So, there you put xi for all I from 1 to n minus 1, and then you put y n 1 to be xn, and for all other entries we put 0. Okay. So, this is the substitution that we are actually doing. So, these are all the new set of variables that we are talking about. So, recall, so this is where the original matrix is there, y1, y1, y2 2 etc., yn n, and then you have this y1 2, y2 3, and then here yn minus 1 n, and then here you have yn 1. So, remaining things are there. From here, so what we are doing, we are just substituting t on the diagonal, and then taking x1 here, x2 here, and xn minus 1 here, and then xn here. All remaining variables we are putting 0. So, this is the new matrix that we are getting. So, now if you write in terms of the elementary matrices, this x is given explicitly as follows. You take the t times identity matrix plus take sum over xi times ei I plus 1, where I ranging from 1 to n. So, you read this I plus 1 is computed modulo n. So, here I plus 1 is computed modulo n, and Eij, that is the set of elementary matrices. Okay. So, now what is the determinant? So, the determinant, you can see that if you are going to take this matrix T t etc. t, x1, x2, and then xn minus 1, and then xn. So, if you look at the determinant of this, and if we expand, for example, using this first row and first column, then you can easily see that this is exactly equal to t times the determinant of this diagonal matrix T T T, and with this off diagonal entry x2 etc. xn minus 1, all other entries will be 0, plus. So, then you will be starting with plus here, minus here, and then you come all the way here, it will be minus 1 power n plus 1. So, then this plus minus 1 power n plus 1, and then you will have determinant xn times the determinant of the rest of these terms. So, you have to forget this So, you have to forget this and then this. So, then it will be determinant of x1, x2 etc. xn minus 1 on the diagonal, and the t will appear here and 0 elsewhere. So, anyway, you get upper triangular and lower triangular matrices, and for which it is easy to compute the determinant. So, you can see that the determinant of this x is going to be t power n plus minus 1 power n plus 1 x 1 etc. x n. So, this is going to be the determinant. Okay. So, now why this polynomial is actually irreducible. So, either you can use the direct definition, it cannot be factorized into product of two polynomials, or you can use Eisenstein's criterion to check that this determinant of x is indeed irreducible polynomial. So, this is irreducible, check. So, now once you have this is irreducible, then it is clear that the determinant of y must be actually irreducible. Why? Suppose the determinant of y is not irreducible, then you will be able to write it as some f times g with the variables these f and g are polynomials in the variables y I j. So, now if this is what happens, then what you can do, you can specialize this y to capital X. So, then on the other hand on the left hand side you get determinant of x, on the right hand side you will get f of x g of x. But since both f and g are homogeneous polynomials, so determinant of y is homogeneous, that implies that both f and g are homogeneous, and that would immediately imply that the specializations f of x and g of x, they are supposed to be non-zero. So, both of them are non-zero, and that actually leads to contradiction, because the polynomial that we computed t power n plus minus 1 power n plus 1 times x 1 etc. x n, that is indeed irreducible polynomial, which is easy to check. And this actually proves that the determinant of y where y is the matrix y I j, that is going to be irreducible. And we will use this in order to prove the factors of this group determinants, they are indeed irreducible. So, maybe I will do the proof of this Frobenius theorem in the next class. I will stop here. Thanks.